Analyzing synchronous counters. A synchronous counter is configured differently than its asynchronous counterpart, where each flip-flop, other than the first, is clocked by the output of the previous flip-flop. The accumulation of propagation delays means that the maximum frequency at which these counters can run is limited. Synchronous counters avoid this problem, with each flip-flop clocked by the same clock signal. No propagation delays mean that the frequency can now go much higher. Let's look at a 3-bit synchronous counter. First, you can see that each flip-flop is connected to the same clock signal. That means they'll all trigger at the same clock edge, in this case, a falling edge. Each of the 3 flip-flops is wired to toggle. The first on every falling edge of the clock, the second when Q0 is high at the clock edge, and the last when Q1 is high at that same clock edge. As you've done before, you can determine how the system behaves using a timing diagram. First, mark in the falling clock edges. Remember that the output transitions can only occur at one of these edges. Knowing that Q0 toggles each time the clock is high at a sample point, you can mark in the waveform for Q0. Show the propagation delay, since it will help you determine the state of Q0 when doing the Q1 waveform. Q1 is wired to toggle each time Q0 is high at a sample point. Marking in this waveform shows a frequency that is 1/2 that of Q0. Q2 is wired to toggle each time Q1 is high at the sample point. You might expect the frequency of this waveform to be 1/2 that of Q1, but it only toggles twice before it returns to a starting state of 0. Reading the waveforms, you can see that during clock cycle 1, the output is 0, 0, 0. During clock cycle 2, it's 0, 0, 1, followed by 0, 1, 0, 1, 1, 1, and then back to 0, 0, 0. This pattern then gets repeated. That means that only 4 of the 8 possible transitions are shown. It's important to understand exactly how the system behaves, so you need to use a tool, such as a state transition table, to identify exactly how the system behaves under any condition. A state transition table defines exactly how a system behaves. Looking at the table, you can determine what the system's next state will be, based on its current or present state. The first column is always an ordered list of the 2 to the n different states in which the system can exist. In this case, n is 3, since we have 3 flip-flops, giving us all the possible states from 0 to 7. Notice that there are 3 columns, each representing one of the flip-flops, and they are ordered with the most significant bit on the left and the least significant bit on the right. Next comes one set of columns for each of the flip-flops. In this case, there are 3 sets that are ordered most significant to least significant. Each set has 3 sections, a J, a K, and a column for a transition. Notice that each of the J and K are identified with the same number as its flip-flop. The first belonging to the last flip-flop and labeled J2 and K2, the middle belonging to the middle flip-flop labeled J1 and K1, and finally J0 and K0, which belong to the first flip-flop. The last column is for the next state. Once the table is complete, it will define the count that will follow the present state identified in the first column. The layout of the table shows you the present state, transition, and next state of each flip-flop in the system, color-coded here to make it easier to interpret. Finally, notice the space that's left above the center columns. Here, you need to identify the logic that feeds that particular flip-flop. To fill in that information, you have to go back to the circuit diagram. You can see that the J and K inputs of the last flip-flop are tied to Q1, so above J2 and K2 on the table, you'll write Q1. The J and K inputs of the middle flip-flop are tied to Q0, so above J1 and K1, you'll write Q0. Finally, both the J and K inputs of the first flip-flop are tied high. That means above J0 and K0, you'll write 1. Now that you know what the logic is for each input in the counter circuit, you're ready to complete the table. Starting in the first set of columns, the ones for J2 and K2, you'll fill in each cell based on the values of Q1. For the first two rows, Q1 is 0. Therefore, both J2 and K2 are filled with a 0. In the next two rows, Q1 is 1, so the cells are filled with a 1. Continuing on, you can see this pattern repeats for the remaining 4 rows. Moving to the second set of columns, you know that J1 and K1 are both dependent on the present value of Q0. In the first row, Q0 is 0, therefore both J1 and K1 are filled with a 0. From row to row, Q0 alternates between 0 and 1, so both J1 and K1 are filled in accordingly. The last set of columns is easy. In both cases, the input is tied high. This means you write a 1 in each of the J0 and K0 cells. Now you must go back and analyze what you have in each pair of J and K inputs. To do this, you have to know how a JK flip-flop behaves. That it holds if both J and K are low, it sets if J is high and K is low, it resets if J is low and K is high, and it toggles when both J and K are high. The first pair of JK inputs are both low. This is the hold state. Mark an H in the transition column. The next row is the same. In the third row, J and K are both high, so mark a T for toggle. Continue this for each of the JK pairs in the rest of the column. Repeat this process for the remaining flip-flops. You now have enough information to determine the values for the next state column. Starting with Q2 in the first row, you have a present state of 0 and a hold. That means the next value for Q2 is the same as its present value, in this case a 0. Moving to the Q1 column, the present value for Q1 is 0. It's to be held, making Q1 next a 0. The Q0 column starts with Q0 low and toggles to a next state of 1. For the second row, Q2 starts at 0 and holds to give a next state of 0. Q1 starts at 0 and toggles to give a next state of 1. And Q0 starts at 1 and toggles to a next state of 0. Each of the following rows are completed in the same way. You can now use this completed state transition table to create a state diagram that defines the system behavior in a much simpler format. To generate a state diagram, you need to extract the information from the present state and the next state columns of your state table. Starting with the first row, the present state is 0 and the next state is 1. That means any time the counter has a value of 0, its next count will always be a 1. This is confirmed by the waveforms you drew. The next row of the table identifies that any time the counter has a value of 1, its next count will be 0, 1, 0, or 2. From 2, it moves to 7. From 7, it goes back to 0. The corresponding state diagram shows these 4 transitions. A count of 0 moves to 1, then to 2, to 7, and back to 0. Each count is represented by a circular node, which is joined to the next node by an arrow. The remaining 4 rows must also be addressed. the first value not in the state diagram is 3. The state table identifies its next state as 4, so you add a separate node for 3 showing that it moves to 4. 4 has a next state of 5. 5 has a next state of 6. And 6 takes the count back to 3. The state diagram is now complete since it describes the full behavior of the counter. So to summarize, when analyzing a synchronous counter, make sure you carefully follow these steps. First, create a state table that has a column for the present state, a set of J, K, and transition columns for each flip-flop, and a column for the next state. Fill in the present state column, making sure you have an ordered list that includes all possible states. Identify the logic that defines each flip-flop's J and K input. Write this at the top of the appropriate column. Determine whether each JK pair represents a hold, a set, a reset, or a toggle. Mark it in the transition column. Determine the next state based on the present state and the specified transition. Finally, draw your state diagram.